Okay, hi everyone. It's 5 p.m. We'll give. Can everyone hear me? Okay, yeah, I adjusted the mic level last time, so let's wait 1 or 2 more minutes. And then there's actually a storm coming in Charlottesville between 5 and 7. So if at any time I lost my internet, then that would be the end of this class today. Okay. One thing I forgot to discuss with you guys last time is office hour. So everyone want the office hour? Okay. So I will set up a doodles pool, and then you guys can fill up the time. So usually I would say I prefer in the afternoon because in the morning it's reserved for me to do research. But we have 5 days a week, so I'm sure we can find some time. Okay. Okay, so let's get started. So last time, okay, we on Tuesday we briefly discussed about a thought experiment that having a lot of electrons, and then examine its color and orientation, and then there we primarily know 2 things. One is that the uncertainty principle does exist, and then the second thing is that to explain some weird probability observation, you kind of have to assume that the electron is wave, right? And then so you can have interference effect, just like the Young double slit experiment. So before we go into quantum mechanics directly, I want to spend 2 lectures introducing the fundamental of waves. The reason of this is that it is my impression that no matter what country you're in, but I think our education on physics and also on mathematics are primarily focused on particles, right? F equals ma. That's kind of what we learned in high school. And then there's not a lot of discussion about waves. And then so because in quantum mechanics, everything we solve is wave equation. So I think it's worth the time to to talk about the fundamental of wave first for 2 lectures. Okay, and then so to discuss. Okay, so to discuss wave, let's first kind of define what wave it is, right? So the wave I'm referring to here, can contain many things like the sound in the air, and then of course, the light wave, water wave, mechanical wave, all type of this wave, and all of these waves, although they are at very different form, but they share something in common, and then we will discuss them. And the fact that we're live streaming this class actually uses at least 2 types of wave, right? One is that I have I'm speaking, so there's sound wave, and then going through the internet, that's the optical wave. And then if you're using Wi-Fi like me, then that's the electrical EM wave at the microwave frequency, right? So there are many waves we use, and then it's worth the time to discuss it. Okay, so before we discuss wave, let's refresh our mind about particle. Okay, particle. This is something that we talk all the time. Okay, particle. So now the question is, okay, let's say particle here and wave here. So if you see a particle and you see it's moving, then mathematically, how would you like to describe it? Right? Think about it. That's probably introduced in the very first class in your high school. So the way that we describe a particle is that we describe its location or its position at a specific time, right? So the description of a particle, for example, if a particle is like moving like this, what we do is that, okay, we say at the time t, the particle is at location x. Right? And we say this x is a vector is because we live in a 3-dimensional world. And then you can have x components, y components, and z component. Okay. And then what causes the particle to move, right? What causes the particle to move? That's, you guys are all very familiar with this. This is F equal ma, right? The equation that you should know, otherwise you wouldn't be in UVA. And then a is the acceleration, which can be written down as the differential of speed, or it's the second differential of location, position. Okay, and then this force can change with time, right? Okay, and this determines the entire motion of the particle. And so if you know the initial position, okay, and then the initial velocity of the particle, and then you know the force at each moment, then the whole trajectory of the particle is determined. Okay, you can calculate it. And here is created a scary thought. Okay, if we 1 second, sorry, there's a disconnection here. Okay, here's one thing that people have thought about. When Newton started this F equals ma thing, right? The thing is that, think about it, if we can decide the motion of every particle, if we know its initial position, and if we know the initial position, initial velocity, we can call this initial condition, then we can decide, then we can calculate where it is for for any time, right, after that, after the initial condition. Then does that mean that if we have a very powerful supercomputer, and then we know the initial condition of the Big Bang, okay, at the beginning of the universe, does that mean that we can predict the motion of every atom, every electron afterwards? In other words, is that if we know that if the supercomputer is powerful enough, it can actually predict my behavior today, that I'm questioning whether there's a supercomputer calculating my behavior, right? And then this is the world we will live in if we don't have quantum mechanics. Okay, the quantum mechanics uncertainty principle break all this. But then if we only have classical mechanics, this is kind of it's kind of a natural result of the Newton system, and that actually, if there's no quantum mechanics and if there's only Newton mechanics, then that actually creates a whole identity crisis for all living things, right? We tend to think that we have free will, right? We have free mind, but then if someone tells you that actually hundreds of billions of years ago, because some interaction among atoms that predict what you would say today and what you would do next day, that's just kind of question the entire meaning of human being or entire meaning of all living things. But luckily, world doesn't run that way. We have quantum mechanics. And also another fun fact is that if you don't have quantum mechanics, you actually won't have Big Bang. Okay, the universe would be really, really weird. Okay, so this is classical mechanics, how you would describe it. And then there's a second thing. First is that the motion of the particle described by position at a certain time, and then the motion of the particle is determined by F equals ma. And then there's the third thing is that if any of you learned analytical mechanics, you know that there's variations of this F equals ma. Okay, F equals ma is not the only way to derive the motion of the particle in classical mechanics. The other way that was built is actually about 200 years ago. It's called analytical mechanics. The thought is this. Okay, the velocity, the position. F equals ma is associated with force and acceleration, right, or velocity. And the velocity is associated with kinetic energy, right? And then the force is associated with potential energy, right? So if I somehow know the energy of the entire system, okay, then by using some mathematics, maybe I can derive F equals ma. And that turns out to be true, and I will give you a quick example here. Is that, think about this system. Okay, there's a wall here, and then there's a spring, there's a box with mass m, and the spring has the k vector. Okay, that's the stiffness of the spring, and then we define this position as x, and then you have gravity as g here. Okay, gravity as g here. And now think about how we can write down the energy for this system. Okay, the energy here we use h. Later you will know this is Hamiltonian. Okay, there are several energy here. The first one is the kinetic energy. You can always write it down. mv squared. Okay, and the second is the potential energy of the spring. Right, if you deviate from its balancing point, then you will store some energy there. So k x minus x naught square, and then you also have a gravity here, and then let's assign this angle as theta. Okay, and then position its project here to see. Project here is to cosine theta minus m g x cosine theta. Okay, so this is the energy of the system. And now let's see, how do we get the force? The force is just a derivative of the potential energy, right? So your force is F equals partial h, there's a negative sign here, and partial x, right? The reason for this is that if you think about how we define work, right, is F times the distance is work, right? So now if you use the energy and do the derivative of position, then you get the force. Okay, it works very well with the original definition. And then you see here, okay, there's an x, so mg cosine theta. And then there's the x, right? So minus k x minus x naught. Okay, and if you take a look, okay, this is exactly the force that is applied on the box along the x direction, right? This is, if your box moves this way, then the string will hold it back, right? And then there's the potential energy pulling it down this way, right? Potential energy, and then you do this, and then yep. Okay, so this is the force. Now let's see how can we get ma, right? The acceleration. The acceleration, you can get it by doing this, right? The only thing that matters with acceleration is speed. So what you can do is that you can first take a look. If I do derivative on the velocity, then what I will get? I will get mv, right? I will get the momentum. Okay, then to get mv to ma, right? What you need to do is you need to second do another derivative on time. Okay, and this way you get the kinetic energy, okay, to ma, right? So the third point here is that to describe the particle moving in classical mechanics, other than using the force F equal ma, you can also use the energy, and then use the equation that often is called either Lagrangian equation or Hamiltonian mechanics. Okay, so this is F equals ma, so this equals that, and then you have a minus sign. You move it here, you get this one. Okay, so these are the three main conclusions, okay, or three main things we need to know about classical mechanics. Okay. Now let's move on to talk about wave. Any questions here? Now the first question about wave is similar. Okay, how do we describe it mathematically? Okay, if you see a wave, how do you describe it? And give an example here. Suppose there's a water wave that start at the center and then propagate and propagate out. Right? You drop a rock, okay, or you drop a stone in the water and then start a wave that propagate out. And how do you describe this wave? Can you track, let's say, individual molecules in this of the water and then see where it goes, like the particle? Potentially, you can do that. That's called first principle. But then it's very inefficient because you have, billions of molecules. Well, billions is small number. Billions of molecules you need to track, right? So that's not really an option. But the other option that you can think about is that what this wave is doing. Okay, if you think about this as a horizontal wave, okay, the water just moves up and down. Just to simplify the argument, then at each location, what you will have is that you will have an amplitude of your water wave, like how much the water molecule deviate from its original position, right? Move up and down, like water up and down. So this can called the amplitude of a wave at a certain location, right? And then for every molecule, in this entire plane, right, they can all move. So to describe a wave, what you really need is that you need to write down a field. Actually, it's called A here. Okay, it's the amplitude of the displacement of the molecules of your wave at the position x and at time t. Okay, so A is the amplitude of the wave, and then it's a function of x and t, right? So if you can write down this function, then you can describe the wave in the entire space. Okay, so first, that's the difference between the mathematical description of a particle and the wave. Okay, this is very different. X is just a function of t in this particle, and amplitude is a function of both t and position. Okay, and there's fundamental difference between these two descriptions. This is mathematically, you can think about this is a single variable. Okay, this is multivariable. And what's worse is that this multivariable x and t is not exchangeable. Right? You can think that you have x, y, z, three coordinate. They are exchangeable because you can rotate your coordinate to move x to y, y to z, right? But then you can never exchange x and t in classical physics unless you introduce general relativity or special relativity. It's because the time only go forward, it doesn't go backward, right? Okay, so this is how we describe a wave, amplitude. Now the second question, which is similar to the classical mechanics case, right? The motion of the particle, or the motion of the particle is determined by the force, F equals ma, or using this. So what determines the motion of the wave? And intuitively, you could say, okay, this is classical mechanics. Of course, it's the force. Okay, it's a force. Now think about this special situation. Think about this special situation. If I created a wave, let's say I poke my finger into a water and then move it up and down, it create a wave that will propagate out, right? And then after a certain time, I stop poking the water. I feel bored, I put my finger out. At that moment, let's say the moment is T2, okay. At that moment, some wave is already propagated very far away from from where my finger is. But at that moment, I stop poking the water, which means I no longer have a force adding to the water. Okay, so in that sense, if we look at the wave already propagated far away here, if I stop moving my finger, does that mean this wave would disappear, or does that mean the wave will continue to propagate? So go ahead. Yeah, continue. Yeah, let me turn up my speaker. Right, based on life experience, right, it continues to propagate, right? Well, one very simple experience is that you can jump into the pool, and then the splash will continue to go regardless whether you're stationary or not, right? If you don't believe this, you can try because it's still summertime, right? Okay, so it looks like the motion of the wave is not driven by, or the propagation of the wave is not driven by the force I apply here. Then what is driven the wave? Propagation. What's making the wave propagate?
I would say the particles themselves, like the nearby particles affect each other.
Yeah, exactly. So, so if you think about this, is that think about the water wave here. Let's say the longitude wave, right? If I push the first particle, first molecule, then this molecule will move a little bit closer to the second molecule, right? And then consider they have a string in between them, right? There's a force. If you push it towards this side, and then there will be a force added onto the second molecule that will let the second molecule to move, right? And then the second molecule will push the third molecule, and the third molecule push the fourth molecule. Okay, so this nearby interaction, or the interaction between molecules, is what causes the wave to propagate. Okay, and that's why we don't have sound in vacuum, right? There's no sound in vacuum. And then also by using this very simple model, okay, you can think about the question: how can we make the wave propagate faster? Right? How can we make that propagate faster? So the idea is that the first molecule should be able to easily push the second molecule to move, right? So the second molecule, or all the molecule, the mass, if it's as small as possible, that would be great, right? It's easier to move. The second thing is that the string, right? If it's very stiff, if it can have a lot of force, then it can, if we move a little bit, then it will add a very large force to the second molecule, and then it can start to move, and move at a faster pace. Right, so you want the mass to be small, and then you want the stiffness, or you want the interaction between molecules to be strong. So because of this, you can kind of predict, okay, the speed of sound in many media. For example, you can think that the water, okay, and the air. The molecule in the water is much closer than the molecule in the air, right? So that the interaction strength is much stronger, so that the speed of sound in water must be larger than air. And then And then if you freeze the water and then it becomes ice, right? You're still using the same molecule, H2O, but then the ice, because it's solid, right? In the solid, well, it's solid because the molecule has strong interaction, so that it's harder to break them, right? So you can also imagine that the speed of sound in the ice is faster than the speed of sound in water. And then if you do a quick Google search, you will see this is 340 meters per second, and then this is 1500 meters per second. This is 4000 meters per second. Okay. And then now, can you guys think about what material will have the highest speed of sound? What media will have the highest speed of sound? A hint is that it's quite expensive. Any guess? Diamond? Right, diamond, right? Because diamond has really strong bond between the molecules, well, between the atoms. It's very hard to break them. And then also diamond has the molecule of atom of carbon, right? Carbon is relatively lightweight. So let's see, right down here, diamond, sound of diamond, the speed of sound in diamond is 12,000 meters per second. And then probably some of you know that the rate that the heat transport is really associated with the speed of sound, right? Because the heat can be considered as phonon is sound. So for a lot of high-end processors or a lot of high-end electronics, we really need to cool down your computation unit, or you really want to cool down your electronics, you can actually use diamond, okay, as a media to dissipate heat. But then, of course, that would be, the budget would be really high, right? So there's actually a lot of study of analyzing the structure of your circuit and then to decide what is the best spot to place the diamond to really accelerate the dissipate of heat. Okay, so now we determined that the interaction, okay, between molecules or between atoms are the reason that the sound propagate. Now the next question is, can we write down an equation of that? Right? Can we write down an equation of that? And some of you might have already learned this in physics class, but then we can really repeat it here. So the way to work on this problem is, a simplest model is actually to use this chain of molecules, right? You can think about there's chain of molecules, and then each of them is connected by a spring, okay, with the constant K, right? So that's the strength of the spring. And then the distance between molecule is delta L, okay, it's fixed it's the same distance between all molecules. And then the mass of the molecule is m, okay, the mass of the molecule is m. Now, for simplicity, we consider the longitude wave, which means the molecule move along this x direction, okay, along this x direction. And then we can assign that the motion of each molecule, the displacement, it move away from its original point is mu, is u, or you can say. So this is ui, the ith molecule. This is ui plus 1, ui minus 1. Okay. So how much it move? Is the text large enough? Can you guys see it? Okay.
Yes.
Okay. Okay, so U is a displacement from this original place. It's not the actual place of your molecule. Okay, so now think about the force. If we take this molecule as example, UI, think about the force it's applied on it, right? The force, there are two ways to have a force. One is that this next molecule, right? If they have a relative motion, then the string will apply a force on it. The other force is applied from the left, right? So the force applied on the molecule Fi can be written down as, say, minus K mu I minus mu I plus 1, right? If your molecule moves towards the right, then the distance is getting closer, then there should be a force pushing you to the left, right? So that's why you have a minus sign here, okay? If both of them move the same amount, then the relative distance is not changed, then you shouldn't have any force. So this is a force on the right. And then similarly, you can write down a force on the left. That's K Ui minus Ui minus 1, okay? And this equals ma I, the acceleration of the ith molecule, and that's m du dt, right? Because ui is the displacement from the original spot, so acceleration is the second derivative of this deviation. Okay. Any questions here? Yeah, go ahead.
So, I guess when you actually have like a wave in motion, that would mean that the sum of the two forces is like it's either positive or negative, right?
Yes, yes.
Okay.
Yeah, so here we only discuss the longitude wave, which means the wave propagate at the same, while the force is along the direction of the wave propagation. Okay, so you can of course have a wave that has a force that's perpendicular to the propagation direction. For example, the string in the guitar or violin, right? They're horizontal wave. They're not longitude wave. Okay. Okay, now let's see how we can kind of organize this. Okay. So first you say you can rearrange the order, and then you can make this ui plus 1 minus ui, and then minus ui minus ui plus 1. Right, we didn't do much, we just flip this one, and then there's a minus sign disappear here. And now let's think about what this is, right? What this is in mathematics, right? In mathematics, remember, okay, all these molecules are very close to each other, very, very close to each other. So this actually reminds you of the differential, right? Suppose you have a function that's yx, right? Yx, this is y, this is x. And then say you want to know, this is yi plus 1, right? You want to know the difference between yi plus 1 minus yi, right? How do you do it? You do it by knowing the slope of this curve at this spot, right? So this is xi. Right, the slope is the differential dy dx, and then this is the difference in y, and this is the difference in x, right? And this is always correct as long as these two x are relatively close to each other, right? And also you can write it down as this one is yi plus 1 minus yi delta x. Right? So now if you look at this, okay, you have ui plus 1 minus ui. Okay, think about ui. Think about u as a function of x, right? It is indeed a function of x because you can relabel this I plus 1 because the I plus 1, I minus 1 has a one-to-one correspondence with the position, right? This one and that one, the distance is delta L, right? So if you move delta L in x, you move from I to I plus 1. Okay, so here the ui plus 1 minus ui, if you use this, okay, think about x as the variable here. X is the variable. Then divided by delta x here, the distance is delta L. Right? Delta L is the distance between these two. Should be the differential between of u on x. Right? And then you say at x equals xi. Okay? And then the same you can apply to this one. This is ui, sorry, this is minus sign here. Minus ui minus 1 delta L equals partial u partial x, x equals xi minus 1. Okay? So this is how you transfer this, indices into a differential which is easier to calculate. Okay? Now if you look at this, okay, you plug this back into here, the force, what you will get is that, okay, this one is the differential times delta L. This is again differential times delta L, but then their indices is different. So you have k delta L, and then u partial u partial x at x equals xi minus partial u partial x at x equals xi minus 1. Okay. Now you can wonder, okay, what is this, right? This is exactly the same way you can calculate this. You can think about this as a new function, and then this function minus the function at a nearby position, right? So the difference between the function value at this spot and function value at the next spot is just the same as the differential of this wave function, okay, the differential of this function times the distance delta L here, right? It's exactly the same as here, but you just take y as partial u partial x. Okay, partial u partial x is your y. Okay, any questions here? Okay, so and then there's a k delta L, okay, from the front. So if you do this calculation, what you see is that you have the force equal to k delta L square partial square u partial x square, okay, the second derivative, equals f ma. Ma is m partial u square partial t square, right? So by doing this kind of a toy model, you kind of get how to calculate the amplitude of your wave. Okay, it's actually a differential equation, and then it's a partial differential equation of multivariable. Okay, And let's write it down somewhere. Let's erase this part.
I have a question.
Yeah, go ahead.
How do you get to m from k delta L squared?
You mean this one?
Yeah.
So, so you see here is a delta U, delta X at position I, minus partial U, partial X at I minus 1, right? And then if you use this, use Y as partial U, partial X, so the way to get the derivative is to divide xi minus xi minus 1, right? This equals the differential of this, or you can write it down as one more step here is and then this one here, the distance between two molecules, this is L, delta L, right? So that this thing up here equals to the second derivative times delta L, okay, times delta L. And then we have done this once here, so this place you already have a k delta L in the front, right? This delta L comes from here. So there's a k delta L, there's a delta L here, so eventually you get k delta L squared. Does that make sense? Okay. The other way
That makes sense. I was wondering about, so then the next step going to n.
Oh, you mean this one? Okay. Oh,
one.
yeah. This one is here, right? F equals ma. And a is acceleration. Acceleration is second derivative of time regarding to the displacement, right?
Yeah, I got it.
Okay, yeah. So another way to check this, you know, when you guys calculate things, especially this differential, it's very easy to not include delta L. And the way to check this is to see the dimension, right? When you start, you see it's k times u, right? This is your unit, kx. U has a dimension of displacement. Now, if you have differential, whenever you have one order of differential in x, you have to add a delta L in the front to keep your dimension the same, right? So you don't even have to calculate. You see, okay, you have second derivative of x, then you must have delta L squared here. And the same apply to here if you because you want to ma, right? So you have to have second derivative of time that get you the acceleration. So you can always double check this result. Okay.
And is this the acceleration of the particles or the wave in general?
The particle. The particle here, yeah, not the wave. The wave itself, in this wave, it actually doesn't have acceleration. Later we'll see this. It actually has a constant propagation speed. Okay, that's why we say, okay, you have a speed of sound in the air or in the water, and then the sound just travel at a constant speed. It doesn't accelerate.
Okay, and what is the difference between delta L and K? Because delta L is the difference between particles and the length in the difference. What is K?
K is the strength of the, it's the force equals Kx, right? That's the spring, right? Consider there's a spring connecting these two particles.
Okay, thank you.
Yeah. Any other questions? Yeah, we're actually going faster every year. It's only 45 minutes, and I think we can stop at 1 hour. And then it's funny, but I usually don't try to over-prepare my class because if I derive all the equation right before the class, then I tend to go really fast, and then you guys will get lost, and then it's not really good. And I actually heard a professor in Harvard. He always said that he doesn't prepare for class at all, and then usually if he doesn't prepare, then the student feel that they're receiving the best education, and then part of the experience is that okay, that professor is actually a genius. He's a full professor at the age of 31 in physics, so they will see okay, actually smart people like him can also struggle on the blackboard, which is quite enjoyable to watch. Okay, and I'm not as smart as he is, but I will also struggle on the whiteboard sometimes. Okay, so now let's look at this. Okay, this equation k delta L square partial square u partial x square equals m. Okay, and this is a terrible equation. Let me say this. This is a terrible equation because there's no way you're going to measure k and delta L, right? It's extremely difficult. Measuring the distance between two molecules and measuring the strength, measuring the stiffness of the interaction strength between two molecules, that's too difficult. So when you have an equation like this, you have to convert it that the constant in this equation has to be something that's measurable for your material. Okay, and the way to do this is to it's actually a little bit tricky. The first is to get the delta L, one delta L here. Okay. And you have a constant like this here. Can you guys guess what this is? You have learned it in high school, for sure. So this is m is the mass of a unit molecule. Delta L is the distance between the molecule, and this is a one-dimensional system. Does this ring a bell? Yes, density, right? One-dimensional density. Okay, this is one-dimensional density. If you push this into three-dimensional, you add other cells in y direction, z direction, this will be a three-dimensional density. Okay, this is one-dimensional density. This is something you can measure, right? Just the density. You don't need to count the number of molecules. You just measure the total mass and then total length of the molecule, total length of your material, and then you get the density. And this one is a little bit tricky, but if anyone knows the answer, please speak out. It's the stiffness of the spring times the distance of the spring. Okay, it's a little bit weird, but then let me ask this question. Okay, each spring.
Does it work?
Sorry.
Does it work?
That's a. Okay, can you say that again?
Elasticity.
I think that's very close. I'm not sure if it's the same. It's just the Young's modulus. Okay, Young's modulus is very similar. So the way to look at this, is that consider there's a spring. Okay, it has the force is kx, right? X is how much you compress or you stretch the spring. Okay, and then now let me ask you this. If you connect the same string, okay, you duplicate this, connect it, and then you connect n copy of it. What is the k of this long string? Each one of them is identical, and there's n of them. Okay, so yeah, this one is usually I find it the difference between two education systems. This is actually taught in in high school in my country, but not in the U.S. So this one, the K is actually K divided by N. Okay, you add another string, and then somehow the stiffness become weaker. Now, think about how this can make sense. Okay, if you only have one string, and then you displace it by delta x, right? Displace it by delta x. The force you get is F equals K delta x. Now, if you compress the same amount for this long string, okay, the total compression of the long string is delta x, then what is the compression for this first string?
Delta x over n?
Yeah, delta x over n, right? Because each string are compressed by the same amount, so that the delta x for the first string is compressed by delta x divided by n, right? So then the force, you can think about the force that the first string has is now F equals K times delta x divided by n, right? That's a force that the force that the first string can have. And then you can say, okay, but you can add the force together, right? No, because the first string has a force to the right to the second one has the force to the left to the first one, so that at this joint point they actually cancel each other, right? And then the only force that you can see here is actually from the first string, right? That's a force when you push it, the force you can feel is a force on the first string, okay? So equivalently, because this whole string compression is delta x, right? If you look at this string, this long string, so what you will see is K divided by N times delta x, right? So this is your new stiffness, right? So if you connect N string together, then your K is divided by N, okay? So how is that connected to here? How is that connected to here? See, I think we can get rid of this.
Isn't this just Planck's law?
Yes, yes. Yep. So so now think about this, right? So the total strength, the K of this long string, okay, is K divided by N, okay? And then what is the length of this string, right? The length is actually delta L, okay? If each section is delta L times N, right? You have N of them. So you see that the stiffness K times the length is actually always a constant, right? It doesn't matter how long your string is, okay? It's a property of the material, right? It's how stiff it is. So this is actually, this part is the one-dimensional Young's module. Okay. So sometimes people write it down as E. Okay. So overall, this equation now become a little bit better now. It's U partial T. Okay, this side, and then equals the Young's modulus divided by the density. Okay. Okay. So this now become an equation that you can use, right? Because the coefficient is not a microscale constant that you need to go in there and measure, but it's actually a material property, right, that you can use. And then later you will see this is actually 1 over velocity square of the wave speed. Okay. So now to make a little bit conclusion here, a small conclusion here is that for the particle, right, for the particle, the way to determine the motion is F equals ma, right? F equals ma, the force. And then for the wave, it's actually by using a differential equation on x and t, right? And then the description is the amplitude of the wave, okay? Amplitude of the wave. Let's see, we'll continue for another roughly 10 minutes, and then I can let you guys go. So next thing we're going to talk about here is a very simple thing, is that when you see an equation, you have to solve it, right? And I guess a lot of you have seen this kind of equation before, right? It's a second order partial differential equation on both sides, and then the solution, depending on the sign of this, right? This is a plus sign. So the solution of this equation is u, okay, right? It's just a sine or cosine wave, right? It's a very simple. This is a standard wave equation, and then your solution is cosine and sine wave, and then you can try to plug in, okay, into here, and then we can actually do that here. Let's use sine as an example, okay? So sine omega t plus kx. Let's use this as an example. So plug in here, and then the derivative of sine becomes cosine, right? And then the derivative of cosine becomes minus sine, right? So the second derivative of this returns to its original form, but with the minus sign. And then every time you do a derivative, the omega come out, right? Omega come out, so you have minus omega squared sine omega t plus kx. That's the left-hand side, equals e divided by rho, okay, the constant. And then look at the second derivative of x. It's the same, right? It's sine omega t plus kx. So sine become cosine, cosine become minus sine, right? So you have a minus sign here as well, and then it becomes sine. And the k come out twice, right? So k squared, and then times sine omega t plus kx. Right. So what you actually get is that you have a sine equals sine, and then the coefficient has to match each other, right? So you have omega divided by k omega divided by k is square root of e divided by rho. Okay, so there's a constraint for these two variables, right? If you have a certain certain frequency, then you have to have a certain wave vector. Okay, certain wave vector. Let's move this equation up, and then okay. So the next thing is, okay, how do you understand this wave, right? it's two variable, right? It's a multivariable function. And the easiest way to think about this is that, okay, if you set x to 0, and then you watch how the amplitude change over time, right? And then you will see a sine wave. Okay, you will see a sine wave. And then the omega is very simple here. The omega is, you see there's a period of your wave, and then in this period, your phase changed from 0 to 2 pi, right? So omega is just the inversion of how much time it takes from the phase to change from 0 to 2 pi, okay? Or the other way to think about it is that the t is a period that the amplitude return to yourself, okay? So the frequency of this wave is 1 over t, okay? And then we know the omega is the angular frequency that can be defined as 2 pi times f, right? So that's the meaning of the angular frequency omega. And then you can do the same thing to learn the meaning of k. So you choose time 0, okay? And then you watch the waveform of along the x direction, right? And what you will see is that, again, you will see a sine wave, right? And then here you will see, okay, the sine wave actually repeats itself after a certain distance, and this is called wavelength, right? This is called wavelength. And then the k, what k is? K is, you can think about, is the frequency in space domain, right? Omega is a frequency in time domain. K is a frequency in x in position in space domain. So here the k is actually defined as 2 pi divided by lambda, right? So when your x changed by one wavelength, the kx will change from a phase to a phase plus 2 pi. So finish one cycle. So this is a definition of k is called wave vector. Okay. Later you will see the connection between k actually with momentum. Okay. And now if you have this, then you can see, okay, omega divided by k, what is it? Right? What is it? So let's write it down. Omega is 2 pi f, so it's 2 pi divided by t. T is the period. And then k is 2 pi divided by lambda, the wavelength. So in total, it's lambda divided by t. Okay. So what is lambda? Lambda is how far the wave travel after one period. Right? That's the wavelength. And what is t? T is how long it takes the wave to travel one period. So here is actually distance divided by the time. Right? The distance you travel is lambda, the time it takes for you to travel is t. So distance divided by time, and this is actually wave velocity. Okay? So wave velocity is completely determined by your material property. Of course, material property depends on temperature, pressure, all of those. It's completely depend on your material property. And then, so that's why I say, okay, some of you ask, okay, F equals ma, what the A is. The A is the acceleration of individual molecule. It's not the acceleration of wave, because a wave actually doesn't have acceleration here. It just has a constant speed in a certain material. Okay. And you can also double check, okay, our previous analysis, whether that makes sense or not. So here is density. What it means is that if your molecule is lighter, right, it has less weight, less mass, then your density will drop. Right? When you drop your density, you will see your velocity go up, right? Velocity go up. And here is the Young's modulus, right? describe the stiffness of your material. So if your material is harder, then also your velocity go up, right? So by using this simple equation, you can actually, check the constant for all the material, and then you can cross-match them whether they actually give you the accurate velocity, and then you can see actually diamond has the fastest velocity. Okay.
I have a question.
Yes.
So this is assuming you have a constant density, but if it
yeah.
wasn't constant, then that would totally change things, right?
Yes, exactly. So so here is like constant density, and then if you don't have constant density, you have things changing slowly, like the distance or the k. If they change, then what you would do is that if it's changing slowly, then these are all functions of x, right? For example, if the left-hand side is less dense and then the right-hand side is denser, that can happen in, let's say, in air, right? It's very, very easy to have that. Or that can actually happen in, you can think about this. This can happen in the ocean, right? When you go down into the ocean, the density actually increase, right? And then this one, well, I'm not sure it's water. So actually, I don't know whether this increase or not. But if you go down, deep into the ocean, that this parameter can change. Okay, so when you solve this equation, when you have a non-uniform material or media, then make sure to include the variables here. Okay, a very good question. Any other questions?
So the point where you replaced k times delta L with Young's modulus, I'm confused how the units check out there.
Oh yeah. so yeah, the confusion will actually come from we're solving a one-dimensional material, one-dimensional system, right? But in reality, all those constants are measured in three-dimensional space, right? So if you check the wave equation in three-dimensional space, you can try to do a Wikipedia, and then you check whether that and that will actually return to the correct Young's module. Does that make sense?
Yeah, but then how do you convert from a three-dimensional Young's modulus to the one-dimensional Young's modulus?
Oh, so that one, let's see. Usually what you do is that you actually you actually establish the equation in three dimensions, and then you say that the wave only propagates in one direction. So the way to think about this is that, okay, if it's a three-dimensional thing, then you will have these terms, right? Okay, and then you say that, okay, the wave only propagates in x direction. The y and z direction is homogeneous. So what you do is that you cross these terms, right? Because they're not changing. Then you're left with a one-dimensional equation. Okay, so there you would see actually the dimension doesn't change, right? Because you're still working with the three-dimensional material, but but the wave is just propagating in one direction. You're still working in a three-dimensional material. Okay, so here we just because of simplicity, right? Because we're not really trying to understand the mechanical wave, right? So that's why we start with a very simple model here. Does that make sense?
Yeah.
Okay. Other questions? Okay. So one final thing to ask you guys to think about here is that we say that the solution is cosine and sine, right? And then you look at this equation. Okay, you can add any amplitude here. And then it's still the solution, right? Because it cancels on both sides. Now you can also think about the linear combination of this. There are actually also mosquitoes. Okay, there are actually also solutions to this equation. And later we'll come back to this point in the next class. Is that the linear combination? Well, we call this type of equation a linear equation. And then one property of a linear equation is that any solution, okay, you can combine them in a linear way, and then there's still the solution. And in quantum mechanics, that we call superposition, and then that's actually one of the key one of the key difference between classical mechanics and wave mechanics. Okay. So that's the end of this class, and then I'll stay here for 5 more minutes. Okay. See you guys next week.
Have a good weekend.
You too.
Hi, Professor. I have a question.
Yeah, go ahead.
I'm not sure if I listened carefully last time or not, but you said like we can do pass-fail rate for this class.
No, well, what I said is that I think eventually, just like last semester, the university will offer you guys an option to do that.
Oh, okay.
Right.
So, but like, yeah. Just like that, everything is come back to normal letter rate, right? It's just like maybe likely that.
I mean, I really hope everything go back to normal, but if we're being realistic, it's not very likely. But anyway, yeah, if that happens, if you guys have to go back home, then I think a pass or fail would be more fair to anyone, for you guys. But then if you guys stay on campus all the time, then throughout the semester, then I think it will still be a ABCD grade.
Okay, thank you so much, Professor.